So now let's go back again to our truth table. A, B, C in sum, carry out. 0, 0, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 1, 1, sorry, 1, 0, 1, 1, 0, 1, 1. Okay, so this is 0, 1, 1, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, sorry, 0, 1, 1, 1. So what is my sum circuit in terms of the min terms? It is summation of min terms what? 1, 2, 4 and 7. Okay, C out is what? Summation of min terms 3, 5, 6, 7. Now what about S bar? Okay, let me write S bar here. This is what? Summation of min terms 0, 3, 5, 6. C out bar. Summation of min terms. C out bar 0, 1, 2, 4. Okay. Now clearly, this is something we discussed earlier. This carry out circuit has the mirroring property. If I invert the inputs, C out also inverts itself, right? So 0, 1, 1 becomes this, and this happens. If I invert 1, you'll get 6. Clear? There's no doubt about it. What about the sum part? If I invert 1, what do I get? 0, 0, 1, you invert, what will you get? 6, right? So this also seems to be inverting. 0 will invert to 7. What about 3 and 4? If I invert 3, 0, 1, 1, I get 1, 0, 0. So that also is inverting. 2 and 5. 0, 1, 0, 1, 0, 1, right? So clearly, conclusion is both sum and carry out are mirror circuits. Yes. It's not always true. Yeah. The necessary condition is there has to be equal number of ones and zeros. Correct. No. Why? If I do just 0 to 7, if let's say I have 3-bit input, 0 to 4 are zeros and 1 to 4 to 4, 0 to 3 are zeros, 4 to 7 are ones. So why should this always be true? That's what I don't understand. Input, yeah. Correct. So simple thing to do is to, if I want to just counter your example, I will negate one of the inputs, 0, 0, 0, I'll get 7. I'll make sure these two outputs are the same, my truth table. Then it will not hold, right? I'm just saying that it's not always true. Only a subset of cases this is true. The necessary condition is, yes, I need to have equal number of ones and zeros in my output. If there are 8 combinations, 4 have to be ones, 4 have to be zeros. Only then that inversion will happen. That mirroring can happen. But it's not always true. Okay? Here it just turns out that XOR, because the sum is an XOR, right? And the carry out is also of the form AB plus BC plus CA, it happens that the mirroring property indeed holds. Okay. So what is my carry out expression now? AB plus BC C in plus C in into A. Correct? So we discussed this in the last module itself. So I'll go straight to the circuit and just implement it in one shot. This is A. We'll come to that. Right? So this, by virtue of mirroring property, I'm going to simply mirror the NMOS network and I will get exactly the same stack on top. Otherwise, you will see that the PMOS stack is going to go up by one number and it will make your logical effort very bad. Right? And what are the sizes now? Obviously, this is just 2, 2, 2, 2, 4, 4, 4, 4. Right? Now I have to assign the inputs, right? Because it's all interchangeable, AB plus BC plus CA, right? I could assign any input anywhere and logically they are all the same. So how do I assign the inputs here? How do I fix A, B and C to the transistor inputs? Yeah? First, tell me the logical effort of, let's say this is my input I0, I1, I2. Okay, so this is also I0, I1, I2. I1, I2, I2. What's the logical effort of I0? G I0. How much? 2, right? 2 plus 4 by 3. What's the logical effort of I1, I2? Yeah, Gi2 equals how much? 4, because I1 is now connected to this 2, it is also connected to this 2. Yeah, 4 plus 4 plus 4, 12, right? 12 by 3 and you get 4. Clearly, one input is going to be faster than the other input, right? Therefore, now amongst A, B and C in, which will you assign where? C in has to be assigned to I0, right? This has to be C in. This can be A, B, doesn't matter. A, B can be, the order there doesn't matter. And obviously this is A and B, A and B. Note also, we have assigned C in to the transistor that is closest to the output. So think about it. When, let's say that this full adder is being used in stage K of the ripple adder, A and B have already come in at time 0 and would have discharged this intermediate node, either this or this node. Now the carry in, it's just waiting for the carry in to come and finish its work. Right? Of course, if the carry had been generated, then what would have happened? This stack would have taken over and settled out to 0 already. If G was 1 for that kth stage, then that carry out would have already got set by this parallel stack here. Right? So we have also accounted for the fact that the signal coming last is connected to the transistor that is closest to the output, thereby having to discharge least number of capacitors in the circuit. Okay, so maybe that's not the right place to write it. Cin connected to least logical effort and transistor closest to output. Okay, now let's come to the sum generation part. What is sum expression? A XOR B XOR Cin. Now can you expand this? And if you were to implement this in static CMOS logic in terms of A, B and Cin, how complex do you think that circuit would be? What's the, just as an exercise, let's first write out this expression, right? It is A times B XNOR Cin, right? Or B XOR Cin bar plus A bar times B XOR Cin. A times B Cin plus B bar Cin bar plus A bar times B Cin bar plus B bar Cin. Yeah? Anyone had a problem here? Have I written something wrong? It's correct, no? Yeah. So clearly you see that, there is A into B Cin plus, so what will be the PMOS stack size? What will be the NMOS stack size? What will be the NMOS stack size? 3, right? Because there is just A, B, C type of terms. PMOS stack size? Yeah, it's basically going to be a very complex circuit. Okay. And therefore it's not, and also you need to have A and A bar now. Only then I can even implement that static CMOS logic correctly. Right? So therefore it's not even wise to go this way. You need A bar, B bar and so on, C bar, and also stack is huge. So now we come back to our earlier discussion where we said it is okay for the sum to be generated a little later than the carry out. While the sum is being generated, the carry out can propagate, no problem. So you actually have time to generate the sum after the carry out has been generated and propagated. Right? What we are going to do is, we are going to see if we can use this carry out that we created in order to create the sum now, so that we can simplify our expression. So now let us look at the expression for sum and carry out bar. Okay, the minterm expression. Sum is equal to summation m of 1, 2, 4, 7 and Cout bar is what? Summation of m 0, 1, 2 and 4. So clearly the carry out bar is equal to the sum in 3 out of 4 cases. Right? So we have to just now take the Cout bar that was generated, by the way, right? And remember this expression that we got here is what? Cout bar. Okay. So we can take that Cout bar and use it as an input to our sum circuit, if I can express the sum in terms of the Cout bar correctly. So it turns out that the sum is basically the 1, 2, 4 is common. Right? These are common. No problem. If it's any of these cases, then sum is equal to carry out bar. No issue. Only in the other cases, I have to create. For example, when the input is 1, 1, 1,
my carry out bar will be 0. But I need a thing for that. So therefore, I have to add that min term into my thing. Okay, so what I'm going to do is, I can say that sum is A, B, C in. Right, this is the min term 7, m of 7. Okay, plus the no, not S, C out bar. Okay, suppose I say this, S is equal to A, B, C in plus C out bar. Will this expression be correct? Why? Which case is it missing? The case, the min term 0. So when the input is 0, 0, 0, I have to kill C out bar. Right? When the input is 0, 0, 0, I just have to kill the C out bar. Then I will get my sum to be the right answer. So this I will simply multiply by A bar, no, A plus B, no, I think, no, A bar, B bar, C in bar. Right? So now what happens is, if the input is 0, 0, 0, then this term equal to 0, 0. Oh, no. It should just be ABC. Yeah, if all three are 0, then it should be 0. You're right. A plus B plus C. Yeah. If all A, B and C in are 0, then this will be equal to 0 for A equal to B equal to C in equal to 0. Then C out bar is also killed. You get the answer to be 0. In the remaining cases, A plus B plus C in will be 1. Because at least one bit will be 1. And therefore the answer will be C out bar. Right? And except that last case, unfortunately C out bar is wrong in the case of 7, min term 7, and therefore that min term alone I am going to add here. Correct? So therefore now I can express this guy, my sum, okay, let me write that here, is A, B, C in plus C out bar into A plus B plus C in. Correct? So all I have to do is take this circuit, and now again remember, on the sum I can do mirroring. Mirroring is still possible. So therefore I am simply going to generate this circuit like this. Right, so this is A, B, C in. And now I'm going to apply my mirroring property here and just mirror that NMOS stack on the PMOS as well. Right, A, B, C in. And I have to create that last case, which is basically A, B into C in. Right, therefore that is nothing but down here. A, B, C in. This is S bar. In order to now generate the carry out and the sum, you basically have to take out these nodes and add an inverter to it. You'll get the C out. and the sum. In this portion, tell me why I did not connect C in to the transistor closest to the output. Huh? Sorry? No, it's not only effect, the logic itself will change. I cannot even do that. See, you can do all this transistor reassignment if it is equivalent to connect any input to any transistor. AB plus BC plus CA was like that. Otherwise, I can't do it. So, C out bar is this thing. And additionally, C out bar will come after C in now. Because C in comes, C out bar gets generated. So, C out bar is the signal that's actually arriving last. So, that is going to the transistor closest to the output anyway. Okay? Any questions here? Yeah. Huh? Yeah. See, basically what we said is the sum is a summation of minterms of what? 1, 2, 4 and 7. Right? The C out bar is summation of minterms 0, 1, 2, 4. So clearly the 1, 2, 4 part is the same. So I can reuse C out bar to generate the sum. Okay? In 3 out of 4 cases. 1, 2, 4. Now, in order to take care of the case of 7, right, I need to add that minterm in. What is the minterm for 7? ABC, right? ABC in. So, I say it is ABC in plus C out bar. But C out bar will give you the wrong answer for minterm 0. Right? So, I have to ensure, because C out bar equal to 1 when the minterm is 0. That is 0, 0, 0. I get a carry out bar of 1. But my sum should be 0. So, in that case, I have to kill the carry out bar. How do I kill the carry out bar? It is basically, I'll tell you what we are doing. Sum is basically A, B, C in plus C out. This will work in 7 out of 8 cases. For the case when A equal to B equal to C in equal to 0, this will be wrong. Because this is C out bar. Because C out bar is 1, but sum should be 0. Right? So, therefore, what do? I just take it and actually it should be this, right? This is my minterm 0. A bar, B bar, C bar is my thing. I have to multiply it by that complement. I'm just killing it. Minterm A bar, B bar, C bar will go high when all are 0. So, if I complement it, it will go exactly low during that time and it will kill the carry out bar. So, this is nothing but A, B, C in plus C out bar into A plus B plus C in. Okay? Any other questions? Yeah. How I used, yeah. That's a very good question. You're asking me if I express a logic function in terms of some other variables, will this mirroring property always hold? Correct. Right. So, I urge you to go back and try it. Okay. Enumerate these inputs. But I'll tell you what the catch is. How many combinations do I have now? A, B, C in, and how many combinations do I have? That's not true, because C out bar itself is a function of A, B and C. And therefore, only a subset of those combinations will work. will actually happen in reality. And this mirroring should hold only for that subset. That's how you get it to work. Okay? You followed his question, right? His question is, I said that the mirroring property, I gave a hand waving statement that here, I said that the mirroring property holds by showing that the sum, 1 goes to 6, 0 goes to 7, 3 goes to 4, 2 goes to 5. Question is, how do you know that the mirroring holds when Cout bar is an input to this function? So now I actually have to, so mirroring holds here. See, mirroring will hold in this expression without any problem, because that's what we showed there. Question is, how will it hold when we do it here? How do I know it holds here? So his point is, you should enumerate the cases and show that the mirroring holds even for this condition. But now Cout bar is an additional input. So how many inputs do you have? You have A, B, C in and Cout bar. But Cout bar is now dependent on A, B and C in. So it's not that it holds, you have to enumerate this for 16 combinations. It's only a subset of combinations, because when A, B, C in equal to 0, 0, 0, Cout bar is 1. You have to enumerate and see that the mirroring holds only for those subset of combinations. So go back, enumerate these cases, find out how many cases there are and see if the mirroring holds or not. Okay?
Cout bar is already a mirror.
Yeah.
So if I invert ABC,
Yeah.
Cout bar also will get inverted. It is same as saying that if I invert ABC, Cout also will get inverted.
Correct.
So the mirroring will hold.
Again, you have to show that. For example, you take this expression here, right? S equal to ABC in plus Cout bar into A plus B plus C. So now I say that, okay, this is S bar is this, S bar is this whole bar. Then you write the Boolean inside, right? Then you can say that when the Cout becomes Cout bar, you can say, okay, that I can invert if my inputs invert. But still you have to show that the mirroring holds, is all I'm saying. You either have to enumerate truth table or you have to show it here. Clear? Yeah. I know, but we have not proved anything like that. Right? So you have to be careful there, is all he was pointing out, and he's right. You have to show that it works for that. Okay? Because it is true. For example, let me tell you, if I give you 4 independent inputs, A, B, C, D, and said AB plus ABC plus D into A plus B plus C, mirroring does not hold there. You cannot do it. It holds only because it's a subset of inputs on which it's going to work. So therefore, you have to show that this still works. Okay?